Okay. We dedicate today to the understanding of the CMOS manufacturing process, how it works, and what are the most important concepts that one has to keep in mind. All the material is taken from this book, chapter 2 of this book, from which we will take a few of the lectures. This is already indicated and mentioned in the course syllabus, and it's a, let's say, general book on electronic systems from a design and from an analysis point of view. So we just take only a few important aspects. Okay, up to now, the only thing that I said about CMOS manufacturing is related to the fact that the process according to which we manufacture silicon integrated circuit is similar to photographic printing, and of course that is too simplistic. Today we are going to look a bit more into the details of the process. Now, I probably already mentioned the fact that in the production of a silicon integrated circuit, you can think of a microprocessor or of a memory chip, or also you can think you can imagine a chip with a very specific purpose. There are two very different phases. One is the design phase, and the other one is the fabrication phase. There are a few companies which have the two phases integrated, and they are typically called IDM, integrated device manufacturers. They design an integrated circuit, and they also manufacture the integrated circuit. And of course, they also do the third thing, which is not typically considered in our courses, which is actually the most important part, the selling of the chips. But at least when we say that a company is an IDM, where IDM is I, integrated, design, D, and manufacturer, is we typically refer to the design phase and the manufacturing phase. For example, just to mention some companies that we have already mentioned here, Intel is an IDM. They design the chips and they fabricate the chips. Also, Samsung typically is an IDM. They design the chips and they fabricate them. And these two are the most important ones as IDM. The most important in terms of let's say annual revenues, so from the economic point of view. And there are different types of companies in the market. One type of company which emerged in the late 90s is the so-called fabless company. A fabless company is a company which only designs and sells the chips, but does not fabricate them. Okay? They typically use another company to fabricate the chips. And for example, at the moment, probably the biggest fabless company is Qualcomm. I think I already said something about this, but it's only good to repeat it in this occasion. So Qualcomm is is a very big company, and more one of the most important in the microprocessor market. But they do not fabricate the chips. Okay, they typically use other companies that are specialized in the fabrication phase. Okay. Well, another company which is actually a fabless company from at least from the integrated chips point of view is Apple. They design the chip, they sell the chip, they use the chip. Basically, they do not sell outside the company. They use them in their own products, but they do not fabricate the integrated circuits. Okay, and this business model of a fabless company actually emerged in the late 90s, and it has been very, very successful because it has become more and more difficult to be able to fabricate very advanced CMOS chips. Okay, just to complete complete the whole range of possible business model. At the end, we have the foundries. Okay, and the foundries are the companies that are only specialized in the fabrication phase. They typically do not design the chips. They take the design from another company. They fabricate the chips, and they provide the chips back to the company that ordered them. Okay, so as you can see, the fabless company and the foundry company have a completely integrated business model. Okay, the fabless need the foundries and vice versa. Okay. Now, why I'm mentioning this? Because actually, it is extremely important, especially if the companies that design the chips and the company that fabricates them are different companies, to have a common interface according to which the designers can pass the designs to the foundry. Okay. Of course, this is important also in an IDM, but it is especially important for a fabless company. The way according to which the design is passed is with a set of optical masks. So basically, the designers design the chip down to the optical masks, which are basically the main recipe that the foundries can use in order to fabricate the chips. All the information regarding the realization of the chips has to be contained in this set of optical masks. Okay? The set of optical masks define exactly how each region has to be treated in the silicon wafer according to the fabrication process of the foundry. Okay? The other important aspect is that, of course, the circuit designers, which are, of course, the engineers that design the chip, and the process engineers, which are the engineers that set up the fabrication process, have to be able to agree on how this information is passed and how the chips will be fabricated. And the way in which they agree on the rules for the fabrication of the chips is through this design rule set, which is extremely important, because the design rule set gives the circuit designs the constraints on how to fabricate the chip. And all these constraints are determined by the technology which is available for chip fabrication. Okay, so this is the framework for this discussion. And now I will go into the details, and so I hope that everything will be clear up to the details. Now, let's look at a very simple and basic CMOS process to understand what are the things that must be treated. So this is a cross-section. So basically, we have taken a wafer in which we have an integrated circuit, and we have just cut it in the middle in order to look at exactly the cross-section. So this is the thickness. Basically, let me just use. Okay, this cross-section represents an inverter, a CMOS inverter. As you remember, in an inverter we have a PMOS and an NMOS. This is the PMOS, and this is the NMOS. Okay, I should help you recognize every single aspect. So, this is the thickness of the silicon wafer, because we are looking at the cross-section. And of course, you remember that the inverter is done in this way. This is VDD, then we have a PMOS. This is the PMOS. And below, in series to the PMOS, we have the NMOS. Okay? This is the input, and this is the output. Now, so this is the NMOS. The NMOS is fabricated directly in this very simple process, directly on the substrate, which is of P-type. If you remember, in an NMOS, we have the channel, which is a channel of electrons, which has to be obtained in a P substrate. So directly the wafer represents the substrates. So this is the source, and this is the drain. You see we have an N plus region for the source, an N plus region for the drain. This is the metallic contact. So this goes to ground. It is this point. GND stays for ground. Okay? When the NMOS is in conduction, we have a channel below, and this is of course the drain. Now, this region here is very thin region, is the oxide, the gate oxide of the NMOS, and this black region here is the here you can read polysilicon. It is the polysilicon gate. The gate is, at least used to be until the initial years of this century, of polysilicon. So it's called metal oxide semiconductor, but actually the metal part was done with polysilicon, which means polycrystalline silicon, very highly doped so that it behaves more or less like a metal. Okay, so this is the NMOS. Then the drain of the NMOS and the drain of the PMOS are connected. Actually, you don't see this part here, but they should be connected by this metal, and they are connected to the output. So this is the output of the inverter. And then this part represents the PMOS. The PMOS must be fabricated onto an N region, but of course the substrate is of P-type. So first, before fabricating the PMOS, one has to have an N region. And this N region is called N-well. It's a large region which is doped with donors so that we have an N-well. So this process is, for this reason, called an N-well process, because there is a specific N-well. Well means a large region of uniform doping, which is required in order to obtain the PMOS devices. And of course, you can recognize here two regions, highly doped for the source and the drain contact. So this is the source. The source region is connected with a metal and taken to the outside, and this is going to be VDD, the supply voltage. And then we have the drain, which is here, and this is the metallic contact to the drain, which is connected again to the output. Okay? And again, this is the oxide, and this is the gate, which is again polysilicon. So the two gates are actually connected. You cannot see here, but in the back of the cross section they are connected because they are connected to the input. So I just probably can use a different color just to indicate something that you cannot see, but on the back these two gates are connected to the input. Okay? So this is how an inverter is mapped onto a physical region. Now, the fabrication process defines, for example, the depth of all these N-wells and all the P+ regions, the N+ regions. So the depth of this region is decided by the fabrication process, and also by the fabrication process is designed the actual doping concentration of all the regions. Okay? Also, the design process defines the thickness of these layers, the oxide layer, the thickness of the polysilicon layer, the thickness of the metal layer, and so on. And also, for example, the minimum feature sizes. The only thing that the designer can actually decide is the geometrical shape from the top. So one can decide how long has to be, for example, this region, how wide has to be the N-well, and so on. And these things are decided by means of the optical masks. So one can draw a design, but actually all these details are decided by the fabrication technology. Of course, the foundry has to give the designers all the information, because depending on the amount of doping and on the thickness of the various parameters, the design has to change accordingly. But this information has to be passed, of course. Okay, this is a very simple process. It is typically still in use, but is pretty old. Let's say it's something from the early 90s. Okay, you should know that for many applications, not let's say high performance digital applications, but for many simple applications, people are still using old processes, because typically old processes cost a lot less to use, and therefore if the type of applications can work also with these old processes, they are going to use it. It makes everything much cheaper. Okay, let's have a look at a more modern process, just to understand what happens. In a more modern process, what you will observe, before I switch the slide, I want to show this part. What you will observe is that the transistors are much more densely packed because, for example, in this process, you see that you do not have abrupt changes of the abrupt interruptions of the layers. You have these very slow varying profiles, and of course they take a lot of space on silicon. In a much more modern process, you have everything much more packed, and so you try to change the thing. Instead of having this abrupt, very smooth profile, you want to have something much more abrupt. And for example, this is one of one example of a modern process. You still have, you still have, no, green is not okay, let me use black. You still have a p-type of substrate. Again, the thickness of the wafer is in this direction. We are still observing a cross-section. But you have to separate P wells and N wells. So you have a dual well process. So this is the P well, and the P well is used to fabricate the NMOS, because in the P well you can have an N channel for the NMOS. And then you have here separated an N well on which one can fabricate a PMOS. So again, this is the PMOS, this is the NMOS, this is the gate oxide. I don't need to write it because it's already specified. On top of it, there is the polysilicon gate, and on top of it, typically there is another layer, which is a silicide. This is typically a silicide. A silicide, for example, titanium silicide, is let's say a compound of silicon with another metal, which is used in order to reduce the resistance of the gate wire. Okay. Again, we have the source here and the drain here. This is the metal region, so this is connected directly to ground, as in the other inverter. Now the two drains are connected together, as we have seen before, and they are connected to the input. So this is going to be the input. No, sorry, this is going to be the output, as we said before. The two gates are connected on the back of this cross-section in order to connect the input. And this is the source of the PMOS, which is connected to VDD. So here we have VDD, and here we have ground, which is the same as here. Okay, so this is the connection that we have. The main things that you should observe as a difference with respect to the other, let's say, type of process, well, there are a few differences. One have been already mentioned. Here we have a double well, a dual well process. Then we have this trench isolation. You see that basically the separation between the two MOSFETs is very sharp. We have, because basically it was possible to create this very deep vertical barrier. This is an oxide. Typically it is silicon oxide, which is used as an insulator to separate the NMOS from the PMOS. You have a very sharp separation. If you look at this other situation, here the separation was this one. Oops, sorry. This was the separation of the oxide. between the NMOS and the PMOS, and you see it was very, very smooth. In this other case, we have a very sharp separation. I don't know exactly why. When I move the slide, when I change slide, the annotation disappears. I don't know exactly why. Okay. Anyway, these are the most important aspects, the aspects that I wanted to highlight. There is another thing that is probably important. You see here we have a different colors also on top of the source and drain regions. We have this purple color here, and also this is a silicide, like the one that we have on the poly, and the reason for the type of additional layer is to reduce the contact resistance. A reduction of the contact resistance from the system point of view has the role of increasing the maximum speed by decreasing the propagation delay. Okay? So, again, also in this case, the fabrication process specifies the level of doping of all the different regions and the thickness of all the different regions. From the point of view of the designer, the only, let's say, degree of freedoms that we have are what we see from the top view. So the geometries from the top. Okay. One thing that is interesting now is to look at the same structure, the CMOS inverter, from the top. Okay, to understand exactly what we see from the top. So we can refer to this situation. So we have two cascaded inverters, a CMOS inverter, the first one, which drives a second CMOS inverter. So in the end, we will have two PMOS transistors and two NMOS transistors. Okay, so the input of the first is Vin. The output of the first is the input of the second. When we say that an inverter drives another inverter, we mean that the output of the first inverter is connected to the input of the second inverter. This is the meaning of drive. Okay? And then the output of the second inverter is the output of the circuit. What is going to be the map of this simple circuit seen from above? The map is this one. This is exactly the same circuit that we have seen before, okay? But this is what is called the layout. And this is what is written on the set of masks. This is the layout. You should be able to recognize the same things that I've shown you before. So let's look at it together. So this is the first inverter. This is easy. First inverter. And this is the second inverter. The different colors represent different types of layers. So this is the input. This is going to be Vin. If you remember, in an inverter, the input goes to the two gates of the two transistors. And this purple line is the polysilicon line. This is poly. When I say poly, I mean polysilicon. Typically one simply writes poly, which forms the gate of the first transistor and the gates of the second transistor. So this is a gate, and this is another gate. First transistor and second transistor. The second transistor, the one below, is the NMOS, and this is the PMOS. Okay? So let's look at these two transistors. They're different in shape, and we should try to understand exactly why. So this is the gate. So below the polysilicon, we have the the electric, the insulator, and below we should have the P region on which we form the N region on which we form the P channel. This is, I just want to highlight the corners. This is the N well. So this pink color is the N well. On which we fabricate the PMOS. This is the source of the PMOS, and this is the drain of the PMOS. So source, gate, drain, seen from above, is the transistor. Source, drain, and gate on the N well. These black squares are the contacts, and the blue line is the metal line. So this goes to VDD. This is connected directly to this metal line, is the metal interconnection. These 4 squares connect the metal interconnections to the N well, and then in the N well we have the transistor. Okay, the drain is connected to this with this square, with this black square, which is the contact, to the other metal, which is the output. So this is the out. Okay, the out of the first transistor, which is connected to the input, you see, to the input of the second inverter. The second inverter is exactly identical to the first one. It is the same structure which is repeated a second time. So the output is connected to the input of the second inverter. This is the second inverter, and this is going to be the output of the second inverter. Okay? So, of course, what we miss now is the NMOS, and this is the NMOS. The NMOS, you see this yellow region here. This yellow region here is the P well. This is the P well in which we have the NMOS transistors. Okay? This is the drain, and this is the source of the NMOS transistors. And there's a contact, this black square, which contacts the drain to the metal. And of course, there is another contact which contacts the source to the metal. So, and every color, every different color corresponds to a different type of layer, because the purple there is the polysilicon. We have seen the pink is the N well, the yellow is the P well, the green. What is the green? The green is actually the green is the active area. This is not something that I have explained. I should discuss it. The green is the active area. And this will be clear a bit later, because actually the transistors are in the for example, the PMOS are in the N well, but they are smaller than the N well. So the active area is the actual area in which that will be occupied by the transistor. Okay? The active area is the actual area in the well, which is occupied by the transistor. And let me finish this point, and then I will go back, because I don't want to lose the notes. So every color corresponds to a different mask. Okay? And so, and basically, the fabrication process has to print a layer for a different type of layer for every color. This is what happens. So the designers have to pass this set of masks, one for every color, and every color corresponds actually to a different type of layer, and therefore different type of process in the fabrication. Okay, just before going on, I just want to highlight what is the difference between this active area and the well. And just let me go back. For example, in this case probably it is easier, also here probably it's easier to understand. This is not probably not the best example, because in this example the active area is exactly equal to the well. Because let me just show you first on this illustration and then on the other one. This is the end well. This is the size of the end well, which is the brown region, and the active area is this opening between the two insulating layer of silicon oxide. This is the active area. And you can see in this illustration they're exactly identical. Okay, so in this case the difference is not significant. This is just a particular case. If we consider the previous one instead, in this case it is pretty easy to understand. This is the end well, the region of the end well, and the active area actually it is this one, because the transistor is in a smaller region. So the active area is going to be this one. So there is a difference between the two things. The transistor occupies a region which is smaller than the end well. Okay. Now, let's consider how everything happens now. So first we need to start from a piece of silicon, of crystalline silicon, which let's say on which the circuit will be fabricated. And we actually start from something which is a silicon ingot. That is a huge piece of silicon. It's a single crystal of silicon. So when I say single crystal, I mean that all the atoms of silicon occupy a very specific position in an ordered ordered crystal. Every atom is in its place, and we have a perfect geometric configuration of all the atoms. This is a huge thing. As of now, if we consider what is typically processed now in silicon foundries, this is something which is, let's say, 1.5 meters long and has a diameter of 300 millimeters. So it's like a pizza, more or less. Okay? And the weight is close to 100 kilograms. So it's a big thing. C'è una grande mortadella più o meno come dimensione, per capirci. And then, I don't know mortadella in English. So this ingot has to be cut in slices, and typically each slice is thinner than 1 millimeter. And then each slice is treated separately in order to fabricate the chips. So you should imagine that on each slice, which is, let's say, which has a diameter of 300 millimeters, you have several hundred chips. If you have a large microprocessor, like an iCore 5, for example, which is more than 1 square centimeter, you still have hundreds of them. But of course, there are integrated circuits that have a dimension of only 3 by 3 millimeters, so that you really have a huge number of chips. And so each each slice is called wafer. Let me write it if I can. This is a wafer. Wafer, really, literally, in the sense of very thin slice. Okay. Now, what is exactly the process that is performed? Let me, before I discuss this so-called photolithographic process, let me show you the end result first. The end result is something like this. This is a photo by Intel of the 2012 generation of processors. So you can see each of them is a processor. You have a tile for every processor, and on the chip you have, let's say, a few hundreds of them. So the wafer is processed at one time, and then at the end of the process, one cuts the wafer into pieces, and each piece has to be packaged separately. Okay? So this is going to be the end result. In order to achieve this end result, we need to repeat this photolithographic process several times. And let's discuss exactly what is going to happen. We typically have to start from here. The first, let me just mention this fact first. Almost all of these steps of the process have to be performed in a so-called clean room. A clean room is let's say, it is described in very technical terms, and in terms of in terms of a class. A class is followed by a number, which is a power of 10 typically. And for example, class 1 means that there is less than one dust particle per cubic foot. Okay? Class 10 means that there are less than 10 particles of dust per cubic foot, and so on. Okay? And this has to be extremely precise, because as you shall see, a single piece of dust on the wafer can completely make the integrated circuit unusable. Okay? Because it can, let's say, a particle of dust is larger than a few tens of transistors, and so the chip is completely ruined. Okay? This is the reason why such clean rooms are needed. Now, the first process is typically the oxidation. The oxidation is performed at a high temperature, the whole wafer in an oven, typically. The temperature is close to 1000 degrees Celsius, and during the oxidation, a thin layer of oxide is deposited on the wafer. After the oxidation, the following step is photoresist coating. And in this case, what happens is that, let's say, typically a drop of photoresist is put on the wafer. Photoresist is a class of polymers which are extremely sensitive to light. Okay, but we are going to see what we do with the photoresist. But at this point, the typical thing is that we need to put a drop of this polymer on the wafer. Then typically the wafer spins a very high velocity so that this drops becomes a layer of photoresist, a very thin layer of just a few microns of photoresist on the whole wafer. Okay? Now, the property of this photoresist is that in the most common situation, we have a so-called negative photoresist. So this means that the photoresist is in principle at the beginning soluble, which means that it can be washed away, but after exposure to ultraviolet light, it becomes harder and insoluble. So it's a very simple property that has been used several times with printing technology. You start with a material that is soluble, but becomes not soluble after exposure to ultraviolet light. And this is why we need the optical masks. The optical masks are some, let's say, thin layers of glass in which we have some regions that are fully transparent and some regions that are opaque, typically are black. So what we do is the following. We take a wafer, we take a mask on the top, and then we illuminate everything with ultraviolet light. So there will be a few regions under the regions in which the mask is transparent that are illuminated by light. And in those regions, the resist becomes hard and not soluble. And then there are other regions over which the mask was black, was opaque, that are not illuminated by light, and then in those regions the resist is still soluble. So this is how we transfer the pattern that we have on the mask on the photoresist. Because after this process, we wash the wafer in a process which is called photoresist development. So we use a solvent in order to wash the wafer, and therefore the regions of the photoresist that are harder remains there, and the regions of the photoresist that are still soluble are washed away. Okay? And in this way, we exactly have repeated the pattern that we have on the mask on the photoresist. Okay? So, after the development, there are a few processes that are not really important. They typically help the transfer of the pattern on the optical mask onto the surface of the wafer. And then at this point we have the most important part. We have the real process step, which can be a deposition of material or can be doping of material, and so on. Typically deposition or doping are the two most important parts. So we transfer the pattern into the structure of the wafer by depositing some layers of material, or by doping some regions, once we have the patterns defined. Okay? After that, we remove the we completely remove all the remaining photoresist, and we start again. Okay, this is the cycle. So as you can see, this part of the cycle from the mask to the process step is typically of a photographic process. It is very close to the way people used to print, to develop a photographic film and to print an image. This is very similar to what happened in those days. And then, of course, the process step is particular and typical of CMOS technology. Okay? This cycle has to be repeated from tens to hundreds of times in the fabrication of a modern silicon chip. So, let's see again this type of process by looking at the at what happens after the various steps on the silicon wafer. So, okay. For example, let's consider one. This is a step, not a stamp. One process step. Let's consider just one of them. And let's follow the various phases. So, first we start with the silicon substrate. So, just a wafer of silicon. Wafer with a thickness of less than 1 millimeter, so very thin. This is just silicon. Now, the only thing that we want to do is define a region in which we have silicon oxide on top and regions in which we do not have silicon oxide on top. So let's follow the various steps. First, we start with a simple silicon substrate. Then we have the first step along the cycle, the oxidation. And after the oxidation, we have this layer of silicon oxide, the purple one. Then after the oxidation, we have the second step, which is so we call it, let me just use the same words. We call it photoresist coating. So we spin the photoresist onto the wafer. Then we use the mask, which is this one, and we illuminate everything with ultraviolet light. Okay? So what happens is that, for example, the mask is opaque in this region, is black in this region, so this yellow part is not illuminated. Under these other regions, the mask is transparent, and therefore the other regions of photoresist are illuminated by ultraviolet light. In other words, we say that the resist is exposed. After exposure, the resist becomes hard, and therefore it is not soluble anymore. Okay? So we are in this situation now. We wash everything with typically with chemical etching. Of course, when I say wash, I use a very simple word. Of course, we do not wash simply with water. We typically wash with a proper solvent, a chemical solvent, or with a mix of chemical solvents and some physical attack, which is what is called a plasma etching. But just to understand the main thing, it's okay if you say wash. We wash the photoresist, and then we end up with only these two regions of photoresist, which is hard and therefore did not go away. Now, at this point, we are ready to perform a process. We want to define some regions in which we have silicon oxide and some regions in which we do not have silicon oxide, because up to this point we have a layer of silicon oxide which is uniform on the whole wafer. Okay? What we do is that we can use some specific chemical process to attack the silicon oxide, but this specific process is blocked by the resist. So, for example, we can etch away, we can attack the silicon oxide with specific acid solvents, and therefore we end up with disappeared silicon oxide when there is no resist, and instead we have, let's say, the silicon oxide which has not been removed below the resist. So we have, basically, as you can see, we have transferred the pattern which was on the mask on the silicon oxide. After this process, we can remove the resist with a specific solvent which is also able to remove the hard resist, but does not remove the silicon oxide below. Of course, for each of these processes, you need chemicals that are only able to attack one type of material and not the other, because otherwise you end up with anything. So, okay, so this had to be done only in order to achieve a pattern on silicon O2. And so, of course, we can repeat the same thing for everything. This was just the position of silicon O2. We have the position of many different materials and also doping. Now, when I said that this cycle has to be repeated between tens and hundreds of times, of course, this is true, especially for the most modern processes. The more modern the process is, the more cycles you need. But many of these steps are recurring, so you have to use them several times. And so it's useful to, let's say, list what are the most important process steps, which are the ones that recur the most. And these are a few of them, let's say, grouped into classes of processes. One, extremely important, is doping. Of course, doping is extremely important because the only way to obtain transistors is to have adjacent regions with different dopings. Okay? This is the way we achieve transistors. There are typically two different ways of doping a material. One is diffusion, and the other one is ion implantation. So diffusion means that typically one puts the wafer in an atmosphere, in an oven, in which we have a gas that contains a dopant at a very high temperature, so the atoms of the dopant penetrate into the silicon wafer. At a very high temperature, the material is basically porous to the dopant atoms. So, for example, if you have phosphorus, which is a typical type of dopant, an atmosphere with phosphorus in which we have the silicon wafer, the phosphorus atom penetrates in the silicon wafer. Okay, and we have a concentration. If this is the silicon wafer, we have a concentration with diffusion which is high at the interface and then decreases along the way. Because, of course, it's easier to penetrate up to here and it's more difficult to penetrate deeper. And the other process is ion implantation. And typically with ion implantation you have a gun, an electric gun, which essentially shoots atoms in the wafer, okay, at a significant energy, so the atoms can penetrate deeper in the wafer, the dopant atoms. And in that case, if you have the same wafer, this is the wafer thickness, wafer thickness. Depending on the energy, you can have a distribution of atoms which is, for example, peaked in the middle of the wafer, or at a position which depends on the energy of implantation. So these two processes are used depending on what you want to achieve in terms of the distribution of dopant atoms in the material. Of course, they are very different because with an implantation you typically cause a damage into the crystal, because you really hit atoms and then you can displace them. So typically after an implantation you need an annealing step, which is a process which consists in putting the wafer in an oven at a high temperature for a few minutes in order to let the atoms go back to their initial position, so that you typically heal the silicon. Now, the important thing of doping is that, of course, you only dope some regions and not other regions. And the trick is that the hardened resist is a shield for dopants. So, for example, if you consider the example that we have seen before, in the regions where you have the hard resist, you do not have doping, because you don't have diffusion through the resist and you do not have implantation through the resist. But instead, the regions which are of silicon, which are exposed, are actually doped. Okay? So, by using the mask, we can decide which regions are going to be doped and which regions are not going to be doped. Sorry. This means that for every type of doping, you need a different mask, and therefore you need to repeat the process again. So one for the N minus, one for the N plus, one for the P minus, and one for the P plus, and so on. So you see how these numbers add up. Okay. Another class of very important processes is the deposition processes. So with deposition, one typically deposits uniform layers of material on the complete wafer. And there are a few types of deposition. One is the oxidation, when we have at the end a layer of silicon oxide. But of course there are other types of deposition. I'm just mentioning them, I don't want to go into the details. We have, for example, chemical vapor deposition, which is very useful for depositing insulators, but also conductors. For example, the nitride, the silicide, and so on, they are deposited by chemical vapor deposition. Then we have the chemical deposition, which is used for depositing polysilicon. And then we have sputtering. So these chemical vapor deposition are pretty simple. You put, I mean, at least in principle, of course, how they occur. You put the wafer in an oven at a high temperature, and then you introduce in the wafer the material that you want to deposit in gas phase. So you have this gas of material that in time deposits uniformly on the wafer. So the thickness of the layer that you have depends on how much time you keep the wafer in the deposition chamber. I said oven, instead is a deposition chamber to be precise. Okay, with chemical deposition, the things is similar, with the main difference that you also have a chemical reaction on the surface. So, for example, in order to deposit silicon, you have to introduce in the chamber this silane, which is a gas containing silicon, and then on the surface, this gas containing silicon reacts with the surface in order to deposit only silicon on the surface. This is why we call it a chemical deposition, because there is deposition from vapor phase, which is followed by chemical reaction. Then you have sputtering. That in that case, sputtering is very, very different. In the case of sputtering, okay, I don't want to discuss sputtering. Let's move on. The sputtering is a process which is useful to deposit metal layers on a silicon wafer. Okay, so there are very many different deposition processes. So we have doping, we have deposition. We also need to have etching. Etching is the definition of 3D patterns. What we did before is a type of etching when we remove the part of the silicon oxide. So with etching, one defines 3D patterns because one removes material only in selected regions. And for etching, we have basically two types of etching. One is called wet etching, and the other is called dry etching. Just let me mention the main differences. With wet etching, one typically uses a solvent, a liquid solvent, in order to remove the material. In the example that we mentioned before, you can use a liquid solvent to remove the silicon oxide, which is not covered with the resist. Okay, this is the example that I've shown you before. The other possibility is to use dry etching, which means instead of using a liquid solvent, we can use typically a gas phase with energetic particles, so that we basically remove in a fast way and in a very anisotropic way vertically only the regions that we do not need. Okay? With wet etching, you have an isotropic etching. You remove everything, a little bit also under the resist. With dry etching, you have very sharp surfaces at the end. Okay. And finally, another process that is very commonly used is a planarization process. Because after all these processes, you typically do not have a flat surface of the wafer. But in order to put something on top of it, you need to have it flat again. And this planarization process is typically a mechanical process that really lets you have a flat surface. Okay, now what I want to do now is to show you how we can use repeatedly these processes in order to have at the end the complete transistor or the complete inverter. So let me show you the processes. So we start from silicon wafer. The first thing that we need to define is the active areas, which means where the transistors are. So every active area is going to be occupied by one or more transistors, and the active areas are separated by this these trenches, so these pieces, these regions of thick insulator, of thick silicon oxide typically. So the active areas where the transistors are, and the field oxide, which is the insulator between neighboring devices, is the region which was colored in yellow in one of the in the double well process that I've shown you before. The yellow region of oxide which separates the two transistors. So these are the first two things that must be done. Second thing, we need to define the well regions with doping. So we need to implant donors in order to obtain the N well, and then we need to implant acceptors in order to obtain the P well. Once we have done that, we need to define the gate stack. For each transistor, we need to define the gate. The gate stack is the sequence of the gate plus the polysilicon, the gate oxide plus the polysilicon plus the silicide on top. They are totally aligned, and one typically has to use just one mouse to define all of them. After the gate stack, one needs to define the source and drain. So one needs an implantation for the source region, the same implantation also for the drain region, and for the substrate contacts, the contact to the substrate. And then finally, we need to put the interconnections. So create the contacts between these regions and the metal lines, and deposit the interconnections. So the sequence is the active regions, the N well and the P well, then the gate stack, the contacts, and the interconnections. Okay? So let's walk through this process again. We start with the wafer. Typically, the wafer actually has this shape, because the initial wafer is P+, but then on top of the wafer, one grows a very pure layer of silicon on which the actual circuit is going to be built. Because typically ones need a very pure material in order to have transistor on. And the wafer, the initial silicon ingot is typically not pure enough. So on top of it, one grows this p-epi, which means an epitaxial layer of silicon. And the only reason is that we need a very pure material. Then after that, we have the deposition of silicon O2, SiO2, which is the silicon oxide. Let's say that is the gate material. And on top of it, we have another layer of insulator, the material which is called Si3 and 4, which is called silicon nitride and is an insulator, but is only used for the process. It will not remain there at the end. Then we have the plasma etching. Of course, we need a mask from that. I don't discuss the resist deposition. You can imagine that if I have a pattern, a geometrical pattern here, it is because there was a proper mask that has been used. So after masking, we need to define this trench. Trench in Italian is trincea, so a very sharp separation between two regions. So we have two different regions, very well separated between them and from the rest. And these two regions, before we go on, these two regions will be the two active regions for the two transistors of the inverter. I'm still discussing the inverter. We need an NMOS and a PMOS. And those two regions will contain the NMOS and the PMOS. They are very well separated as of now. Then one fills the trenches with silicon oxide, this black layer. Of course, silicon oxide is an insulator. In order to deposit silicon oxide, one has to remove the silicon nitride. So what's the reason for silicon nitride? Why I just used it? Yeah, this is something that I did not explain in detail, and it is just that in order to do the trenches, I need the silicon nitride because the region, first I attack the silicon nitride and then one obtains the trenches, and the silicon nitride acts as a mask for this etching of the trenches. So these are the two regions. Then once we have it, we need to dope the two regions. First, we have the N-well. You see, we have to use a mask to open a region in the resist for the doping, and then to perform an implantation of the N-well in this part. So this is the resist. From here to here, of course, we have performed the whole cycle. So we have deposited the resist, then use a mask. We have opened this window in the resist, and then we can perform the implantation in order to have the N-well. And then we do it again with another mask on the other side in order to have the P-well. So at this point, what we have is the P-well and the N-well. The silicon oxide layer is very thin, so that is simply traversed by the ions that are implanted in the silicon without any problem. It is basically transparent to the atoms. Once we have the N-well and the P-well, then we can deposit the polysilicon gate. So the oxide was already there. We can deposit the polysilicon gate, and this pattern is obtained with another mask. So we will have a PMOS on this side and an NMOS on this other side. At the moment, we only have the gate here, the gate contact. We still need the source, the drain, and of course the gate oxide has only to be below the gate, but not also on the other regions. So we first have to remove the, we need to remove the oxide. Before removing the oxide, we perform the doping, because we have already seen that we can perform the doping even if we have the oxide. So, and you see here we do not need another mask, because the polysilicon will act as a mask for the implantation of donors here for the source and drain contact of the PMOS, and following implantation of acceptors for the P plus regions of the source and drain of the PMOS. So this is what we have at the moment. We have defined source, drain, and gate of both the PMOS and the NMOS. And then we need to remove here the insulator which is not below the gate. And then after it, we deposit an additional insulator and perform some holes in order to contact the source and drain of the two transistors. Okay, so from here to here, first I pattern the silicon oxide and remove the silicon oxide which is exposed. This is easy because the silicon oxide that I want is already below the polysilicon gate. So with a solvent for silicon oxide, I simply remove these very thin layers of silicon oxide. Then another thick layer of silicon oxide to separate the transistors from the rest, and then I have to open some holes in the silicon oxide to make the contacts. Then we can deposit a metal line, this is aluminum, in general a metal, to have the contact of the source with the drain, with the ground. The two drains together, which are connected to the output, and the drain and the source, sorry, of the PMOS, which has to be connected with VDD. In this metal layer, I need to open two windows in order to separate the three different contacts that we have, because this has to be connected to the ground, this has to be connected to the output, and this has to be connected to the supply voltage. Okay? And then, well, again, this is just to connect to everything to a second metal layer. So this is going to be ground, this is going to be output, and